So just looking at a couple of them off the test. Number 2, 11.375 into binary. In our binary, we have the 1s, the 2s, the 4s, the 8s, and the 16s. It goes up by multiplying by 2 as you go to the left. Or it's 2 to the power of 0, 2 to the power of 1, 2 to the second, 2 to the third, and so on. Going to the right of the decimal point, every time we move one spot to the right, we divide by 2. Or the power goes down by 1. So 2 to the negative 1 is 1/2, or 0.5. 2 to the negative 2 is 0.25, or 1/4. 2 to the negative 3 would be 0.125, or 1/8, and so on. So 11.375, well, we've got an 8 out of that. So there's 3 left. There's no 4s. There's a 2, which leaves us with 1. And there's a 1. Notice I've ignored the decimal so far. I deal with what's before the decimal point and what's after the decimal point separately. I have 0.375 left. Can I get a 0.5 out of that? No, I cannot. Can I get a 0.25 out of it? Sure can. So that leaves me with 0.125. Well, I get a 0.125 out of it, and that's it. I'm done. So that is that number in binary. So just continue down the line, subtracting out. Number 4 was a little bit more difficult. 312.875. Now remember, here, this is the 1s, 16s, 256s, and so on. 4096 would be this next one. Every time we move one space left or right, we're multiplying or dividing by 16. So when we go this way, this is the 16th, or the 0.0625 spot. That's as small as we need to go here. So looking at this, we can get a 256 out of here, only 1. So that's going to be what? 56 left. We can get 3 16s, which would be 48. So there's 8 left, and 8 1s. So we've got 138. Now we've got that 0.875. Well, a 16th, let's see what happens when we take 0.875 divided by a 16th, or 0.0625. We get 14, which is E. So it's 138.E. Any questions? Okay. It's 16. Yeah, for octal it'd be 8, and I didn't put any octal on the test. Yeah, hexadecimal is 16 as you move each space. This would be 1/256. Remember, these will always mirror these, reciprocals. Really, there isn't, I don't know of any real practical applications for decimal, hexadecimal. I mean, there are some for decimal binary, because you do have to encode decimal numbers electronically. So they do use decimal binary, but most of the time when they do binary coding, they use the ASCII code. I don't know if you ever heard of that, the ASCII code, where each, I'm trying to remember, I believe it's a, yeah, so 0 is 0, 1 is 1, all the way up to 9. And then 10 is A, 11 is B, small letters, and then you got capital letters, and then you got the symbols. And I believe it goes from 0 to, is it 512? No, it's not. It might be 128. There are 128 symbols in the ASCII code. We can check it out quick. Okay, so anyway, So we're going to take a look at, well, we're going to do a little bit of review of powers. Of course, we know that x to the third power means what? X cubed, and then x times x times x. 3x's multiplied together. If I have 8 to the third power, do you guys know how to type that in your calculator? Okay. 512. Using, most of you, I believe, probably have the caret key. Looks like that. Yep. Okay. So, a little race to see how you do. 5 to the 6th power. Yes, you are correct. Okay. So if we have x to the 4th times x to the 6th, what's that give us? X to the 10th, exactly. Because x to the 4th is 4x's multiplied together. X to the 6th is 6x's multiplied together. If I multiply them all together, I now have 10x's multiplied together, so x to the 10th. So the shortcut, when we are multiplying two exponents, this, by the way, is what we call an exponent. And an exponent has two parts. The number here is called the base. That's the number that's being repeated in the multiplication. And this is called the power. That's telling us how many times it's repeated. So whenever we are multiplying two exponents that have the same base, like y to the 9th times y to the 12th, we can add the powers. This becomes y to the 9 plus 12, or y to the 21. So how about z to the 13th times x to the 5th? Why didn't I add the powers? They have different bases. Remember, we said they have to have the same base to add the powers. So we can only combine the powers if they have the same base. So how about x to the 5th divided by x squared? X to the 3rd, very good. Because this is x to the 5th is 5x's multiplied together. X squared is 2x's multiplied together. And if I treat it like a fraction, I just cancel out two of them. I'm left with x to the 3rd. Now, of course, the shortcut when we're dealing with exponents and dividing is to do what with the powers? Subtract. 5 minus 2 gives us 3. So if I have y to the 18th divided by y to the 11th, I'm going to get y to the 7th. Oh, good question. So what if I have x to the 5th divided by x to the 12th? What's 5 minus 12? Negative 7. What does that mean, really? X to the 5th is 5x's multiplied together. I'm kind of regretting using x to the 12th right now. But anyway, x to the 12th is 12x's multiplied together. We cancel out like that. Well, everything on top is canceled out, so that's just 1. On bottom, we have x to the 7th. 1 over x to the 7th and x to the negative 7th are equivalent. Now you might be wondering, well, how can something be multiplied by itself a negative number of times? Kind of like with negatives, the basic definition of multiplication breaks down when you're multiplying two negative numbers. So we look for a pattern. So if I'm looking at something simple like 5 to the power of 4 is 625. 5 to the power of 3 is 125. What's 5 squared? 25. So now I've established a pattern here. When I start out with a base of 5 in my exponent, If I reduce the power by 1, what happens to the number? Well, it divides by 5. Right? This is divided by 5 because I reduced the power by 1. If I keep going and I reduce the power by 1 again, 5 to the power of 1 is 5. Does that fit the pattern? I reduced the power by 1. Did the answer divide by 5? Sure did. So then what is 5 to the 0? 5 divided by 5 would be 1. It has to be 1. A lot of people want to say 0 for that. It is anything to the power of 0 is 1. If I go 5 to the negative 1, well, I divide by 5 again, that's 1/5. 5 to the negative 2, well, dividing by 5 again, 1/5 divided by 5 is 1/25. 5 to the negative 3, 1/25 divided by 5 is 1/125. And so on. You'll see there's a connection between these negative powers and the positive power. 5 to the negative third is 1 over 5 to the third. It's the reciprocal of 5 to the third. So if I have x to the negative 10, that's the same as saying 1 over x to the positive 10. What's a little trickier to grasp is this one. 1 over x to the negative 3. Let's go x to the positive 3. So if you think about it, this is 1 over x to the negative 3 is 1 over x to the third. 1 divided by 1 over x to the third is 1 divided by 1 over x to the third. Becomes 1 times x to the third over 1, which is x to the third.
Somebody takes all of his notes and every class.
Waits till the board gets full and takes a picture? Yeah. Nothing wrong with that. Sure. You bet. This works even if you have multiple variables. Now we said if we have different bases, we can't combine them, but we can take it one variable at a time. We've got x to the fifth, y to the third, times x to the fourth, y squared. I can separate it out and do the x to the fifth times the x to the fourth, which will be x to the ninth. Y to the third times y squared is y to the fifth. Same with division. X to the eighth, y to the seventh, divided by x to the fifth, y to the ninth. And divide out the x's. X to the eighth divided by x to the fifth is x to the 8 minus 3, or 8 minus 5. 3. Didn't give that one away though. Y to the seventh divided by y to the ninth is y to the negative 2. Very good. So when we have more than one variable, we can just go each variable separately and combine them. How about x to the fifth to the third power? There you go. That's saying 3x to the fifths multiplied together. Each x to the fifth is 5 x's. Which means, yes, there's a total of 15 x's. So this is x to the 15th. So if I have y to the 11th to the power of 8, that's going to be y to the 88th. And the same goes with multiple variables. I can have x to the 4th, y to the 9th, z squared to the 5th power. This is going to be x to the what? 20th. 4 times 5 is 20. Y to the 45th. 9 times 5 is 45. And z to the 10th. Very good. We've already kind of hinted at this one. X to the negative fourth, of course, is 1 over x to the fourth. Just like 1 over x to the negative seventh is just x to the positive 7. So what if we combine things? Just for fun. Remember, we have to do what's in the parentheses first if we can. Can I do anything with the x's? X to the negative 2. You got it. How about the y's? Y to the 11th. 8 minus a negative 3 is 8 plus 3, or 11. So now to the power of negative 5, y to the negative 2 to the power of negative 5, or x to the negative 2 to the power of negative 5 is x to the positive 10. Negative 2 times negative 5 is positive 10. That's going to be y to the negative 55. Y to the negative 55. What do you think? Coming back to you a little bit? I enjoy watching people suffer, so it's fun for me. There's a relationship between these powers and our roots. Remember, we kind of discussed a little bit, operations come in pairs. We've got addition and subtraction that go together. Multiplication and division go together. They reverse each other. Well, powers and roots go together. X squared, the square root of a number, undo each other. And they follow the same rules. One thing I would stress in the first semester of this class is that adding and subtracting are really the same thing. Just one's going forward, one's going backwards. Same with multiplying and dividing. Same operation, just forward and reverse. A power and a root are the same operation. If I take 5 to the power of 3, what do I get? 125. If I take the third root of 125, I get back to 5. Those two operations reverse each other. So when I'm dealing with a root, like the square root of xy, when I did x and y squared, I could do x squared and then y squared, right? I could do each variable separately. Same here. The square root of xy can be treated as the square root of x times the square root of y. I can separate them out and do each piece separately, just like I could with the powers. If it's the fifth root of xy, I can do the same thing. That's the fifth root of x times the fifth root of y. Let's say I have the fourth root of x divided by y. Same type of thing. I can separate that out and do the fourth root of x over the fourth root of y. I can apply it to each piece separately, just like I did with my powers. If I had this x squared over y to the fifth to the power of 3, I would do x squared to the power of 3 is x to the 6, 2 times 3, over y to the fifth to the power of 3 is y to the 15th. With my roots, I'm going backwards. Let's say I have the fourth root of x to the 12th over y to the 20th. When I did a power, I multiplied the powers. What do you think I'm going to do when I do a root? Divide the powers. So x to the 12th, what am I going to divide the 12 by? 4, the fourth root. 12 divided by 4 is 3, so that's x to the third. Y to the 20th is going to become y to the 5th. So I apply the root to it separately. If I take the 18th root of 27,843 to the power of 18, what is my answer? Okay, now, hold on. Let's say I do this. Let's say I take 3 times 12, and then I divide by 12. What do I get? 3. So you're exactly right. The 18th root and the power of 18 cancel out. This is just 27,843. If I have an equation that is the third root of x equals 5, to solve that, if we had 5 times x equals 30, how would we solve that? We divide by 5, because multiplying and dividing are opposites, right? Here, what's the opposite of a third root? Power of 3. So the power of 3 cancels out, leaves me with x. 5 to the power of 3 is 125. So x to the power of 125, or x equals 125. Or if I have x to the 5th equals 3,125, what's the opposite of x to the 5th, or to the 5th? 5th root. X equals, what's the 5th root of 3,125? You guys remember how to do that in your calculators? Type in 5, then you have to hit the x root key. 3125 would be 5. On yours, Hunter, you hit 5, then you hit second, and then it's the caret key. Okay. What's that? Okay. So the 5th root of 7, the 5th root of 7 to the power of 5. The 5th root and the 5 undo each other, right? Well, if I had like 3 to the 4th power to the power of 5, what would I do with those powers? I multiply them. I get 3 to the 20th power. So here, I have something going on here. 7th to some power, I'm going to call it x, to the power of 5. This is 7 to what power? To the power of 1, right? Yeah, this is just 7 here, right? So this is x times 5 equals 1. So what does x have to be? 1/5. So a 5th root, the 5th root of 7 is the same as 7 to the 1/5. You guys just did the 5th root of 3,125 and found it to be 5. So I want you to try this. Type in 5 to the power of 1 ABC5 and see what it comes up. Or not 5, sorry. 3,125 to the power of 1/5. What does it give you? 5? So a root and a power are the same thing. Like the square root of 9 can be written as 9 to the power of 1/2. Or the 4th root of 81 can be written as 81 to the power of 1/4. Very good. So, what's that? It is. Well, we can have, let's say we have something like this, 27 to the power of 2/3. This is giving us two things. There's two pieces of information here. The top, the numerator is a power. The denominator is the index of a root. So this here can be interpreted in two ways. One, this can be 27 squared and then take the third root. Or two, it can be the third root of 27 and then squared. Either way, you're taking a third root and you're squaring it. If I do the third root, oops. I do the third root of 27, then I square it, I should get 9. If I do the third root of 27 squared, I'll still get 9. Another consequence of this, since we said the square root of x times y can be split up into the square root of x times the square root of y. Some textbooks will do this. Now, for you guys, it's not terribly important, but if you were to go on to a bachelor's degree at some point, you would see this. They might take something like the square root of 20. They would split 20 up into 4 times 5. So they make this the square root of 4 times the square root of 5. Square root of 4 is 2, so this is just 2 times the square root of 5. Looks familiar? If you had Algebra 2, you probably saw that towards the end of an Algebra 2 class. In the math world, they consider that to be simpler than this. The main reason it's considered to be simpler was back in the day before calculators, which wasn't that long ago. I mean, I've never known a life without a calculator, but if you go back to like the 1950s, they didn't have electronic calculators. Well, they had some, but very few electronic calculators. So you'd have to look up that square root in the table. Well, you didn't want to have a table that had every number from 1 through whatever. So you just did the prime numbers. You know, 1 is 2, 3, 5, 7, 11, and so on. Was all you had in the table. I got to be careful. There's a little bit more than that, but you had the ones that weren't perfect squares that were in the table. So instead of having to have 20 in there, you could just take the square root of 5 and multiply it by 2. It was relatively easy to multiply by 2. So it just saved them room in their tables is all that really did for them. So I want you guys to do this for me. Find for me trying to figure out what I want to put in here. 625 to the power of 3/4. Now I know you can punch that in your calculator and get a number. But I want you to do this for me. I want you to write for me the root first with the power, or the power first with the root. Does that make sense? So here you got the root and the power, here you've got the root and the power. How would you express that either way? So up here, what's going to go in here is the index of my root. 4, it's the denominator of the fraction. What's going to be my power? 3, the numerator of my fraction. So down here, index of my root, 4, and my power, 3. Now I realize your calculator will actually accept it. You can actually just type in 625 to the power of 3/4, and it will spit that out as 125. Why are we dealing with this? Well, because the next thing we're going to talk about is something called exponentials. In an exponential, instead of having x to the power of 5 equals 32, how would we solve this for x, by the way? Not square root, but fifth root. So the fifth root and the power of 5 cancel out. We got x. Fifth root of 32 is 2. Well, what if instead of x to the fifth equals 32, what if we've got 5 to the power of x equals 625? We're taking a number to the power of our variable. Well, this is what we call an exponential, where the variable is the power. It is in the power, we should say, because there might be more there. To solve that, we don't want to take away the power. Here, we did a root because we're trying to get rid of the power. Here, we're dealing with an exponent, but instead of getting rid of the power of the exponent, we want to get rid of the base of the exponent. To get rid of the base of the exponent, we're going to use something called a log. Now up here, this was a power of 5, so we had to have a root, a fifth root. Here, the base of our power, or our exponent is a 5. We've got to have a log base 5. The log base 5 and 5 to the power of x cancel out, and we're left with just x. So you've got log base 5 of 625, which is 4. When you guys come back from your conference, this is what we're going to be talking about, is exponents. So for today, I'm going to hand out a packet, and in this packet, page 464 through 465, 1 through 43, the odd, deals with these rules of powers and rules of roots. I also want you to take a look at page 469. We have not discussed this yet. Excuse me. 1 through 25, the odd. This is what we're going to discuss when you guys get back. But I want to see just what you guys can do on your own. Gives you something to think about over the 2 days when you had all your free time at the conference, right? Yeah. If you don't get time to get to that part, don't worry about it. That's what we will go back over when you guys get back.